I'm Dr. Benjamin Watts from the Paul Scherrer Institute, and I am a beamline scientist on the STixxam instrument, which is part of the Swiss light source synchrotron. Just quickly about the institute. Paul Scherrer Institute is at the north of Switzerland, close to the border with Germany. And it's a research institute with quite a large variety of large-scale facilities for material science. So we have neutrons, muons, protons, and photons that we can throw at your sample. So pretty much anything you want to learn, one of these types of probes is going to tell you something about it. I'm going to be focusing on X-ray photons, specifically soft X-rays, which are very useful for understanding organic materials. So the talk today will be about the spectromicroscopy of organic materials. So we're combining spectroscopy and microscopy to learn about the materials that make up our sample. We'll talk a bit about things in general to begin with. Then we'll talk about how a scanning transmission X-ray microscope works. And then we talk a bit about what we can do with the data to really tease out all of those details that we want to learn about our samples. And then just quickly talk a little bit about the STixxam. So generally, there's a whole spectrum of photons that we can use, from radio waves through microwaves, infrared, visible, through ultraviolet, and then the X-rays and even gamma rays. And the only difference between them is the wavelength of that type of radiation. Now, because of these wavelengths, they interact with different types of things, and they interact with the matter in different ways. So for the largest things, it's just macroscopic conductors, so an antenna of some kind. Then as we get to the infrared, we start to interact with molecular vibrations and rotations. In the visible and ultraviolet, we start moving the valence electrons around. And then in the X-rays, we start interacting with the core electrons in the light elements, and then towards the harder X-rays, the core electrons of the heavy elements. And these are quite powerful for research because they have a kind of simplicity to them, and that you can really use to tease out a lot of details that are otherwise very complicated for other probes. So when you're working with photons, typically people just think in terms of either imaging or spectroscopy. But the reality is that you're always dealing with all of these things at the same time. They're always there in some way. It's just that perhaps you're trivializing them. So if you're using, say, an electron microscope and you're doing imaging, there is some spectroscopy going on, but you're trivializing it. So it is just black and white images that you're getting. Similarly, with spectroscopy, you're getting energy information, which can be turned into imaging if you start scanning that probe around. So these things can be sort of combined in various ways. So the focus today is going to be on real space imaging combined with photo absorption of X-rays. So to get into spectroscopy, what we will be looking at mostly is photon absorption. So basically we have a certain amount of X-rays arriving at the front of the sample and fewer X-rays exiting out the rear. We can use Beer's law to turn the amount of transmission that we observe into what we call the optical density. So the kind of the part of the spectrum, or the representation of the spectrum, that combines linearly, so that things get a lot more simple, because the absorption rate is exponential, whereas in terms of optical density, it is linear. So that's why we have the logarithm in Beer's law there. Now, when we look at the X-ray absorption spectrum in general, we see that the absorption rate decreases as we increase the photon energy or make the wavelength shorter. And this we can sort of see in the harder X-rays being more penetrating, so they go through materials more easily. So if you think about the classic medical X-rays, These are very hard X-rays. They travel through the flesh, and it's the elements in the bones that really absorb those X-rays, and so we're penetrating through. If we use softer X-rays, so lower energy, then we don't get that same penetration anymore. So on top of this general more penetrating power, we get these absorption edges, and these occur when the photon has enough energy to interact with a deeper shell of an element. So if we look in the lower right of the screen here, we have the spectrum of something that's vaguely organic, and we see a jump at the carbon 1s, and then another jump at nitrogen 1s, another jump at the oxygen 1s, and then a small jump at the fluorine 1s. And these are occurring at energies specific to those elements, because that's the energy needed to liberate an electron from those core shells of the elements. And because the elements are very quantized, these are very clear and distinct. So we're not seeing any interplay between the different elements here. So if we look closer, what happens is an X-ray is absorbed by an atom. The electron that's sort of closest to that sort of resonant energy can either be ejected from the atom entirely, in which case you have a photoelectron, which people doing XPS will be quite familiar with. But you can also get an electron promotion. So it moves from this 1s state up to an unoccupied state. And then this leaves the atom excited, and then later an electron can fall into that core hole that's left behind, and the energy that's left over is given to either a fluorescent X-ray or an Auger electron. So we have a number of processes going on here that are all started by the X-ray absorption. And so we have a few different modes of being able to detect that this absorption happened. We can look at the X-rays being removed from the probe beam. We can look at fluorescent X-rays being created, or we can look at electrons given off by the sample. So in terms of the unoccupied electronic states that these electrons can be put into, for organic materials, these are typically the antibonding states. So when we have two atoms come together, the states will split, and they will form a lower energy bonding orbital that the electrons will go into to form a bond, a covalent bond, and an antibonding orbital, which will remain empty. So for carbon, these are the 2p electrons that do this. And so we get the sigma type bonding state and a corresponding sigma star antibonding state. And in the pi orbitals, we get the pi bonding states and then the pi star antibonding states. So these go together. So when in MXAFs we see a resonance, this is the electron going from the core 1s shell up to these antibonding states. And if the antibonding state is present for the electron to go into, then that bonding state must also be there. So although we're not directly detecting the bonding states, we are detecting something that is very closely connected to that. And so all of the peaks that we see around these absorption edges, we can assign them to different types of bonding that's present in the molecules. So here we have a few examples of some molecular structures, like polystyrene has a lot of phenyl rings, and because of this, it gets a very strong pi star resonance peak at this energy of about 285 electron volts. When we have a carboxyl group, we get a peak at about 288 EV. And of course, with CH bonds for just a linear alkane, then we get these bonds at about 287 for carbon-hydrogen sigma bonds. So we'll generally talk about the types of bonding that are present, or we talk about pi star and sigma star resonances. And these are, intrinsically linked. So we're essentially talking about the same thing. So for biological materials, especially with plants, as the Treesearch and FibRe would be interested in, we're mostly looking at biopolymers. And so biopolymers tend not to have quite so much structural variation as synthetic polymers, because you have the same kind of motifs repeated over and over again, but with lots of randomization. So what we're really looking for is the ratio of resonance peak heights, which indicate the proportional amount of different types of bonding. So we can see here that lignin at the bottom of the graph, the plot, it is clearly different from the other polymers here in that it has a very strong peak at 285 EV. And as I mentioned with the polystyrene, this is due to the phenyl ring. So the pi star antibonding orbital of the phenyl ring has an energy here, and we see the structure of lignin has quite a lot of these phenyl rings in it. Whereas cellulose has lots of rings, but there's no double bond, so there's no pi star orbitals present, and so there's no peak at 285 EV. However, we have lots of other types of bonds, and so we get other resonance peaks. And by looking at the ratio of these peaks, we can narrow down what kind of material we are looking at. So for the carbon edge, we can see quite a bit of distinction. We can do the same kind of thing at the oxygen edge on the right-hand side of the screen here, but we see there's a lot less variation. And this is because oxygen is a little bit more squishy in the way that it does bonds. It can move around more, so it has a bit more variety in the energies. And so that kind of broadens the peaks out. And also it doesn't have such complicated hybridization schemes as carbon. So it's just a much simpler elements and spectra to be looking at. So typically, you don't see quite as much detail in the oxygen edge as you do in the carbon edge. And even if you're trying to differentiate two materials where one has no oxygen and the other one has some oxygen, you're typically better off looking at the carbon-oxygen resonances in the carbon edge than you are looking at the oxygen edge, just because the carbon edge, has so much detail there. Typically, I mean, for every oxygen, you're going to have a carbon atom there. So you're going to get just as much, and you can collect it at the same time as you get other kinds of information about carbon. So when we're talking about organic materials with X-rays, the carbon edge is really the place where all the interesting stuff happens, and where 99% of the research is focused. So moving on now from spectroscopy to microscopy, there's a few different ways that we can do microscopy with X-rays. The big limiting factor is the zone plate lenses for focusing. X-rays are quite difficult to focus. And so this is the core of all of these microscopes, is trying to utilize this kind of work around this kind of problem. So the instrument I use is a STixxam, a scanning transmission X-ray microscope. And here we have a zone plate lens which focuses on the sample. So we essentially illuminate a single pixel of our sample. And then we have a detector that's just a point detector. It simply looks at how much light comes through, and it's not an array, doesn't make a picture by itself. It's just one number. So it's very, very simple. And to make an image, we have to scan the sample back and forth. And to measure a spectrum, we have to scan the monochromator of the beamline to change the wavelength of the light, which is the fact for all the types of X-ray microscope, actually. And then the other kind of X-ray microscope is the transmission X-ray microscope, also called a full field microscope. This is a lot more similar to the visible microscopes that most people are familiar with, in that you illuminate a sample and then you have an objective lens to magnify this image onto an array detector. Now, this kind of microscope is possible, and there are some of them around. However, the zone plates are quite low efficiency. So we're talking about 20% is 20% efficiency is a good zone plate. And this is positioned after the sample in the case of a STixxam, and therefore your sample will see 5 times as many photons as the detector does, which means that the radiation dose your sample receives will be automatically 5 times higher, at least, than what you would have in a scanning microscope. So that's really the big problem there. Another issue is that the magnification and focusing is affected by the positioning of these objects. And when we change the photon energy, the zone plate will change its focal length. So to keep everything in focus, we have to move a whole lot of objects. For a scanning microscope, we only have to move the zone plate, and that's enough to keep it in focus. This is quite easy to automate. For a full field microscope, we have to move at least 2 things. So there's the distance before and after the objective lens that we have to take care of. And this is a lot more difficult to do well. And so spectroscopy becomes a much bigger problem for there. A new idea is tychography. And here we basically replace the optics with mathematics. Typically, we use a zone, kind of a bad zone plate to illuminate the sample. For technical reasons, you just want something that has a very strong imprint on the phase of the beam. And then you measure the diffraction pattern, and you scan the sample to measure the diffraction pattern from overlapping regions. And then you can use some complicated maths, which basically boils down to something like a Sudoku puzzle, to figure out what the real space image is. This is really cool in that it gets around the limitations of focusing of the zone plate, but you need a really good low noise detector, which doesn't really exist for the carbon edge yet. So we can get down to about 600 electron volts, and then things are kind of working okay. But anything lower than that, and it's really not working very well. There's also issues with spectral distortions. Because there's some guessing going on, you don't get a nice spectrum. So most of the work has gone into the imaging side of things. And there's reasons why things work out quite easily, but for spectroscopy, it's a lot more complicated, and they can't use the same tricks to solve them. So tychography at the moment is wonderful, but for organic materials, it's not really ready for prime time. STixxam is definitely the way to go. So to look a bit closer at a STixxam, we have a zone plate focusing on our sample. And then we have this auto-selecting aperture, which is essentially just a piece of metal with a small hole in it. And we position that hole so that the focused light goes through and any unfocused light gets blocked. And then we have a detector at the back, which is usually a phosphor screen with a photomultiplier tube. So a zone plate is a diffractive imaging optic, and its spot size is limited by the width of the outermost zone. So we have a whole bunch of these rings put together, and however well we can make that outermost zone tells us what spot size and therefore resolution we can get. Typically, we have something like 30 nanometers resolution. And the focal length is a couple of millimeters. It depends on the photon energy and the outermost zone width of the zone plate. So as the zone width gets smaller, the light gets brought in with a larger angle, so a higher numerical aperture. So we get higher resolution and shorter focal length. Our record at the moment is 8.8 nanometer zones, and this gave us a resolution of about 7 nanometers. But this was kind of a hero effort, and you should not expect to get this good a resolution for your research unless you are willing to make very big compromises. Typically, about 30 nanometers is what you should expect. So in terms of scanning, we have here the design of the STixxam. We have the zone plate on a Z stage, so it can move back and forth to accommodate the changing focal length when we change the photon energy. The auto-selecting aperture, we can move in X and Y to position that pinhole on the axis of the zone plate. And then the sample has a coarse Z stage underneath, which moves both the sample and the detector in Z. So we can move all that sort of away from the zone plate to change the sample easily. And then the sample has a coarse XY stage and a fine XY stage. We separate this because we need to have a reasonable translation range. So our coarse stage can go a centimeter or two, whereas the fine stage, we need that to be very fast and precise. For that, we use a piezo scanner with a range of, say, 30 microns. And then the detector stage, we just need to, again, position that on the optical axis of the zone plate. So once that's set up, then we don't really have to do anything to do that in operation. My cat is snoring. I hope that's not too distracting. So for the scanning, we are using physical stages. And if you look at anything closely enough, it's essentially made out of jelly. And you can't trust it to be precise or even stiff. So what we do is we use position metrology to really get very precise measurement of where things are. So here we use something called an interferometer, where we bounce a laser beam off a mirror on the zone plate stage, off the zone plate stage and off the sample stage. And then we recombine those beams to get interference. And from this interference, we can tell how these things are moving relative to each other. And so we can use that to give feedback to the scanning stage to hold the position better. And we can also record those positions to use later. So if we don't get the position we asked for, we at least know the position that we got. And so we can use that to fix glitches in our scanning. So on the left here, we have an image where we had some lines where, as we're scanning across X, the start position was off by a bit. And so we can see that line of pixels is just shifted. So because we measured the positions for each pixel, we can use those to reinterpolate the image and remove those glitches. So the resolution of this interferometer is much, much better than the spot size of the zone plate. So compared to the resolution of the zone plate, our positioning is essentially perfect. And it includes any thermal drifts, so we don't have to worry about things drifting over time. We really know where things are. And then finally, the detector, as I said before, it's just a phosphor screen with a photomultiplier tube behind it. So the X-rays excite the phosphor, which give off visible photons. And these are guided into the photomultiplier tube, where they create a cascade of electrons. And then those electrons are pulsed at a piece of electronics called a discriminator can look at and decide whether a spike is big enough to be a real photon count instead of just noise in the electronics. And then that is sent to the computer to say, hey, we saw a photon, let's add that to the count. So now we've talked about imaging and spectroscopy, and now we want to start talking about what we can do with combining these things. So essentially, we have high resolution images with spectroscopic contrast. This contrast can tell us about elemental composition just by where the absorption edges are. It can tell us about molecular structure by looking at the resonances of the carbon K edge, telling us what antibonding orbitals are present. For other elements like, say, iron, we can tell the oxidation state. And these spectra combine linearly. So if you have two materials present, then what we observe is just the sum of their spectra weighted according to whatever the proportion of those materials are present in. There's no interactions or anything to complicate things. So what we have are quantitative color images. We have a number of color channels in the energies that we choose to measure our images at. So we have three-dimensional data cubes here. So then the question is, how do we analyze this? So we have a few different methods, and these are implemented in the Mantis program, which you can get at spectromicroscopy.com. So we start with our with our I and I0 measurements. So the I is the transmission through the sample. The I0 is how much arrived at the front of the sample, which we measure by just looking at an empty region of the sample. So you just kind of move next to the sample. We combine these with Beer's law to get the optical density, and then we have our data in a format that's where we have the spectra linearly combining. And then we have to ask ourselves, do we know what materials are present and have their spectra? If the answer is yes, then we can measure those reference spectra and do a singular value decomposition to get the component maps. So then we have the sort of percentage composition in each pixel of those images that we took. If we don't know them, then we can do some other complicated mathematics, which is quite easy to apply. If you just follow the program, we have principal component analysis, which looks at, breaks down how the spectra vary throughout the measurements, and then cluster analysis to try and group them together into something that's easily digestible by humans. And then from that, we get the same kind of component maps and cluster spectra. If our measurements include regions where the materials are pure, then those cluster spectra can be the same as the reference spectra that we would have gotten from measuring those. But in a lot of biological materials, you're not going to see pure examples of those materials. So the cluster spectra will tend to look like the most extreme mixtures that it can have. So if you have something that's 99% pure, then that's what will come up in your cluster spectra. So to go into these in a bit more detail with an example, here is something that I've worked with in the past. This is a synthetic polymer. This pair are F8BT and PFB. These are conjugated polymers, and so they have semiconducting properties, which makes them useful for electronic devices like FETs and solar cells. We can see the structures have a lot of phenyl rings, but there's a little bit of variety between them. And in the spectra that we see underneath, we see that PFB has a very strong pi star peak, whereas the F8BT, its pi star peak is split into shorter, fatter component peak, largely because of this benzothiazole group here, where the nitrogens and sulfur sort of pull the electrons away from the phenyl ring and change the energy a little bit. So you don't have lots of phenyl rings with the exact same energy, but they get shifted a little bit to the side of each other. So then if we measure images at specific points in the spectra, so we have 280 EV, which is what we call the pre-edge, so before carbon is strongly absorbing. And then we have 320 EV in the post-edge where carbon is strongly absorbing. And then from these, we can basically tell how much carbon is present and how much of other elements might be present. And then to differentiate the two components, we have these two measurements at 284.7 and 285.1, where the PFB is absorbing strongly, or just before that absorption kicks in, and we have a shoulder from the F8BT absorbing significantly more strongly than the PFB is. And so when we look at these two images, we see that the contrast is flipped. because we've switched which component is doing the absorption. So here we have just the straight images, and we want to separate that into a percentage composition. So we do that through something called singular value decomposition, which is basically matrix multiplication, and then we invert it to get the answer. So the first array is our reference spectra. So we have the PFB and the F8BT at the measured energies. And then we have our unknown quantity, so how much of those are present. And then we have our measurements. And then we solve this for X. There's software that will do this for you. And we need to have at least as many energy measurements as there are material components to solve for. So technically, just 2 measurements is enough. But if we oversample, it helps to reject noise and we get a better result. And so here we see percentage composition and also thickness maps. So through the trace, we can see that the thickness varies. So we have here a strong PFB rich domain and then an F8BT rich continuous phase. And we see from the cut through that the PFB rich phase is thinner. So we can see there's a correlation between those. And this comes from an artifact of the spin coating method used to produce them. And then also we can look at different blends. So that's a 1-to-1, we have 5-to-1 and 1-to-5. And we can see that the shape changes and the composition in those domains also change. So this is important for producing a solar cell, perhaps, because we need to know how much of these are blended together, because we need the interface between the 2 materials to separate the charges when it absorbs a photon. So this is important information for understanding how these materials form a device. So looking at a biopolymer example, we have here an SVD analysis of a lentil stem section. And here we have measurements at particular energies for lignin, cellulose, and resin. And we can see that at those energies, those particular materials light up brighter than the others. And then when we do our composition maps, we can make a sort of a 3-color map, and we can see from the color what the percentage composition is of each part. So we can see the lignin tends to be forming here between the cells, and then we have the cellulose lining the cell walls, and then the resin tends to fill in between. So if we don't know the spectra, then, as I said, we can do principal component and cluster analysis. And basically what this is the PCA looks for spectral variety. So first of all, the first eigenspectra it will find is basically the average of the whole image. And then the second one is a spectrum which you can add or subtract from the average to get most of the others. And then it's sort of like a Taylor expansion. It gets smaller and smaller components as you go on through the eigenspectra. And we can see that the eigenvalues associated with these drop in magnitude quite quickly. And from the images, you can see that they really go towards noise at the end. So we can see here in the spectra and the images, the initial components show structure that looks real, and then the later components just show noise. And it's up to a human to decide where that cutoff is, because there's no algorithm that can really do that efficiently. So once we've done that, we have a way to understand the variety, but it doesn't tell us what the different components are in our material. So we do what's called cluster analysis. So we look at how these eigenspectra fit the measurements in each pixel, and then we map those out in a multi-dimensional array for each component to see how they separate from each other. So here we see in the upper right some illustrations of how these different clusters are spread out. And there's an algorithm that will sort of draw boundaries between them and say how they're separated. And then from that, we get a map showing where these different clusters are spatially located, and we get the spectra of what they are looking like. So there's a lot of mathematics here, but basically it ends up doing something very similar to the SVD. It's a bit more difficult to say exactly what these clusters are. So the singular value decomposition is definitely preferable if you want to really understand the chemistry of what's happening in your sample. So for a Norway spruce section, we have here, again, we see some cells. We can see there's resin filling the space, the void within the cells. And we can see that the lignin and cellulose-rich regions have been identified by the principal component analysis and cluster spectra. And we can see this worked at both the carbon edge and the oxygen edge, and we can see the variations in the spectra, and we can analyze the peaks that we see here to get further information on what types of bonding is present in those spectral regions. So that's how things work in general. To do this, you need to go to a STixxam, which will be located at a synchrotron. There's quite a few of these around. If you just do a bit of searching on Google, you'll find a few of them. There's one in Sweden called Softimax. There's also some in Berlin and Paris and Oxford. And so ours is in Switzerland. It's called Pollux. And these are all run as a user facility. So basically they exist for people like you to come and use them. So we give away 70% of the operational time to people who apply for it. In our case, it's a simple 2-page proposal, and there's deadlines twice per year. The success rate is about 50%. It's competitive, so we have a committee that rank them through the most interesting to the least interesting, and we just give away beam time until we run out. We teach you how to use the instrument. It's point-and-click interface, quite simple to use, and remote operation is possible, which was very important during the COVID period. So that's to come and use the instrument. So aside from the basic things, we can also access lots of other elements. And so if you want to know, say, the oxidation state of one of these elements that's present in your sample, then we can, if it fits within our energy range, then we can do some measurements there. We can also do more fancy things. So we have this in situ cell where we can expose a sample to gas of varying, say, humidity and temperature. So we can look at something like water uptake in a sample. This has been used a lot by a group at PSI for looking at atmospheric particles. So say particles of smoke and sort of organic things that are thrown into the air by sea spray, and looking at how these are affected by ozone. We can also look at materials in water. So the carbon edge is within what's called the water window. So we can seal a solution between two silicon nitride membranes and then image what's happening in between them. So while we normally do measurements in vacuum, we can also do measurements in a gas environment or in an aqueous environment. And with that, I'd like to thank my co-workers, Jörg Raber, Peter Alpert, and Simone Finizio. And I go to Josephine for questions.